Well, welcome to video lesson number 5, where we're going to review some things about atomic structure. Now, the idea of the atom goes way back to ancient times and Democritus, but really it's been in the last couple hundred years where we've actually understood something of the internal structure of the atom. Dalton proposed that atoms were indestructible particles with no actual internal structure. And that idea progressed with Thomson and his experiments with the cathode ray, where he basically found the subatomic particle called the electron. But he envisioned the atom and the electrons as embedded in a sphere of positive charge, kind of like plums and plum pudding, or we said like chocolate chips and a chocolate chip cookie. And then Rutherford, when he did his experiments with the gold foil and shooting the alpha particles at it, he fully expected, based off of Thomson's model, that these particles would go basically straight through the gold foil. And surprisingly, what happened was that 1 in every 8,000 bounced back at an abrupt angle. So Rutherford concluded that he must have hit something, a dense region where all the mass is, and it must be a real small area, since only 1 in 8,000 actually bounced back. And of course he called this the nucleus. And then surprisingly, most of the atom then is empty space occupied by electrons. Now, how are these electrons arranged? Well, our understanding of that really progressed when Niels Bohr proposed his model of the atom based off of experiments with atomic spectra. Remember, his idea was that the electrons are arranged in energy levels in discrete circular orbits as they move around the nucleus. So Bohr's model was correct in terms of the electrons being in energy levels, but in terms of the exact position of the electron, it turned out to be a little bit more complicated. And so with the work of Heisenberg and with the mathematical equations of Schrodinger, it was shown that you can't know the exact position of an electron. All you can say is where it's probably located. And that's where we brought in the orbital model, or the electron cloud model, also called the quantum mechanical model. And in this next slide, I'm just contrasting the Bohr model, or the planetary model. You can see the electron moving around like a planet moving around the sun, versus really the electron cloud model or orbital model. So that electron is moving around. The darker regions of the graphic there show where the electron is more of the time. The lighter regions where it's less of the time. Again, it's a region of space where you're likely to find the electron. Now, I went ahead and gave you some ways to picture the atom in terms of we drew them in class. So let's go ahead and do it. Okay, so this is in your notes. We did this in class just as a review. This example is for cesium. Remember the atomic symbol, things we can gain from that in terms of the information. The atomic numbers, the number on top tells us the number of protons and the number of electrons in a neutral atom. This number down here is the atomic mass, which is an average mass of all the isotopes. It wouldn't hurt to review our subatomic particles real quick. This is on your review sheet. Of course, we have protons, neutrons, and electrons. Protons have a charge of +1 and a mass of 1. They're located inside the nucleus along with the neutrons. Their ratio determines the stability of the nucleus, which we talked about in our unit on nuclear chemistry. Neutrons have a charge of 0 and a mass of 1. So again, all the mass is in the nucleus, yet it consists of very little of the actual space or volume of the atom. It's more like a dime inside of a football stadium, was the illustration I gave you. So this right here, that's way too big, but it's just the way the picture is, okay? What we want to focus on now is how are these electrons, our third subatomic particle, arranged in the atom. And remember, they have a charge of -1 and a mass of basically 0, okay? So the electrons are arranged in these energy levels. So this is energy level 1, for example. This is energy level 2, 3, 4, and 5. And then I gave you these electron configurations so you can see how they are arranged. Now, the derivation of this, or where these actual numbers come from, we could figure out, like we talked about in class, based off the S, P, and D orbitals. But I basically just gave this to you so you could just get an idea of how the electrons are arranged. So we have 2 in the first energy level. Remember, electrons fill the lowest energy levels first, then we move outwards. Second energy level, you can see, has 8. So I'll underline that so you can see 2, 3, 4, 5, 6, 7, and 8. The third energy level, remember, can hold up to 18 electrons. That's because there are d orbitals at the third energy level if we think about our quantum mechanical. So that was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We also have 18 in the fourth energy level. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And of course there is 1 in that last energy level. In this case it's the fifth. Now you might be thinking to yourself, wow, that's a lot of electrons, but really it's the electrons in the outermost energy level called valence electrons that determine the chemistry and the physical properties basically of the element. So in this case, in the fifth energy, that would be our highest energy level, there is 1 electron. That's the valence electron. That's super important. So I gave you another way of drawing atoms called Lewis dot structures, which basically highlight this. You simply write the symbol, and then you write dots corresponding to the number of valence electrons. So in this case, cesium would have 1 dot. And that's a very simple yet effective and powerful way to represent the valence electrons. Okay, and so that brings us to our second model, the orbital model. Now, what we have here is a better representation of what the atom actually looks like, though it's not perfect. But basically, this model, remember, combines the s and the p and the d orbitals into one picture, so I like this, okay? Remembering that the s and the p orbitals will hybridize during chemical bonding, and so we call them sp3s. So we kind of, on this picture, draw them as one orbital, but really they're 2 separate. But for simplification purposes, that's how we're drawing them. Okay? So remember the electron configuration for cesium, again, this is cesium, is 2, 8, 18, 18, 1. Okay? And so we would fill the diagram as follows. So 2 electrons would go in that s sublevel, the first energy level. Remember, first energy level has 1 sublevel, the s. Second energy level has the s and the p, which hybridized into these sp3 orbitals right here. So these are sp3 orbitals, and we have 8. So remember, they fill each orbital first, one at a time, because electrons want to be alone, they're negative charge, and then they will pair up if they have to. Even though we draw them next to each other like that to save space, they're really moving around in this region of space, which we described. Remember, the S is spherical, the P is more dumbbell shaped, and again, the D is clover. And we don't get to the D until we get to the third energy level, right? So anyways, here we go on to the third energy level. Notice that there are 18 electrons. How can those 18 electrons fit? Well, that's because, again, there are those D orbitals. But the sp3s will fill up first. So there's our 4, 5, 6, 7, 8 electrons, okay? And now those other 10 go in the d orbitals. Again, we put 1 electron in here at a time because they'd rather be alone. These are the d orbitals. And now they start pairing up, and that's how we get the 18 in the third energy level, because of those d orbitals. Okay? The fourth energy level also has 18, so we would fill that in like this. There they go. Now they start to pair up. And now we start to go into the d orbital. So one at a time. And now we should have, after I get done pairing them up, now we have 18. Okay? And that leaves us 1 in that valence orbital, which is the 5th energy level on sp3 in this case. Okay, we then studied the periodic table and related that to atomic structure. So for example, the periodic table is arranged by atomic number, and when we looked at that, we saw that there are a number of patterns or trends that observe for different physical properties, namely atomic size, electronegativity, and ionization energy. And I told you I want you to know the trend up and to the right, but also I want you to understand why the trend exists based off your knowledge of atomic structure. And to help you out, I gave you a reminder about the octet rule. Remember the rule of 8, that all atoms want to have 8 valence electrons to look like noble gases. Helium would be the exception with 2. And then the first rule of chemistry, which simply states that opposite charges attract. So plus and minus attract. Whereas like charges, plus and plus repel, minus and minus would repel. The effective nuclear charge is the amount of positive charge in the nucleus, which is important to keep in mind. And that is simply the number of protons represented by the atomic number. And then one other concept was this idea of electron shielding, and that electrons can actually block other electrons at different energy levels from feeling the positively charged nucleus. So with that, we are ready to understand. Okay, so our first trend, atomic size, you can clearly see that it decreases as I go up and to the right, or it increases as I go down and to the left on the periodic table. Now the easier one to explain is the up and down. Just remember that the up and down is not explained by the atomic mass, because that's the size of the nucleus. The size of the atom is determined by the electrons arranged in these energy levels. As I go down a group, for example, I'm getting more and more electrons in more energy levels, thus the atom gets bigger. So if I compare, for example, fluorine and chlorine, fluorine has 7 valence electrons, but 9 total electrons. Those valence electrons are in the second energy level, whereas chlorine has 17 electrons. Those 7 valence electrons are in the third energy level. So clearly, as I go down, I'm getting bigger. As I go up, I'm getting smaller. Now, the harder of the two trends to explain was that as I go from left to right, the size also decreases. And we said you can explain that because what happens is you go from left to right, although the numbers are getting bigger in terms of the atomic mass, the number you want to focus is on the atomic number, which represents the number of protons. Because as we go from left to right, we're getting more and more positive charge, and when I'm within a period, the electrons are at the same, basically, distance away or energy level from the nucleus, and thus, because there's more positive charge, the atom constricts or is smaller. Okay? And so I gave you this little illustration. If this is the nucleus where the positive charge is, and we're watching a concert, and we're all arranged in the same energy level or position, and we have this guy playing, right? That's not so exciting. That doesn't get my attention versus a rock and roll band. Now I'm really into this. Now I'm paying attention, right? So that gets our attention. What gets the attention of a negative electron? The amount of positive charge. So that's why an atom, when there is more positive charge, the atom will actually move in, assuming those electrons are in the same energy level. Okay, so here we have lithium. Again, an electron in the second energy level. Notice there's 3 positive charge. If I compare that to something on the far right, like the periodic table, like fluorine, for example, fluorine has 9 positive charge, yet those electrons are the same energy level or distance away. Because there's more going on, that gets the attention of the electrons, and a positive and negative attract, bringing the size of the atom in and making it smaller. Okay, the next trend we looked at was electronegativity, and that also goes up and to the right, but notice that it increases. So there's something to say about the size of the atom and its ability to attract electrons. And basically, the smaller it is, the better it is at attracting electrons. And again, that's what electronegativity is, the ability to attract an electron. So as I go this way, the electronegativity is increasing as the atomic size decreases, and electronegativity is also increasing as I go to the top because the atomic size is decreasing. So just the first rule of chemistry, better attraction between plus and minus as I go up and to the right. We also said you can look at that in terms of the pattern versus metal versus non-metal. So remember, this is my metal, non-metal boundary. On the left, I have metals, they're losers. On the right, I have non-metals, they're winners. So in terms of the octet rule, a metal wants to lose electrons to get octets, whereas I move to the right on the periodic table, I'm moving towards more and more non-metal-ish. They want to gain electrons to get the octet. Now that's also the reason why noble gases have an electronegativity of 0. Even though they're to the far right on the periodic table, they do not want to attract electrons because that would mess up their octet. They would no longer have 8. For example, they might have 9 if they attract an electron. Okay? Now the last trend we looked at was for ionization energy. That trend followed electronegativity and increases as you go up and to the right. Remember, electronegativity is the ability to attract an electron. Ionization energy is the energy needed to remove the electron. So it should make sense, the more I'm attracted to the electron, the harder it is to remove it, or the more energy will be needed to remove it from me. So those trends go together. The only thing to keep in mind is that noble gases have a high ionization energy because for the octet rule's sake, they don't want to lose their electron because then they wouldn't have 8 anymore. For example, they might have 7. So I hope that was helpful. Do your review sheet. Good luck on the